So let's take a look at how the branch is determined in the pipeline. So here's our typical processor pipeline, and in which stage here do we actually apply the outcome of the branch? Well, we can take a look at this and we can see what happens here. Here's the path that comes back from the branch decision and chooses the next PC. And you can see where this happens. This happens in the memory stage. So we compute the result here in the execute stage. We don't actually do anything about it until the branch instruction gets to the memory stage. When it gets to the memory stage, then we choose the next PC. So let's try and practice this. So we've got a bunch of questions here, and we've got an example program. So the program is going to go through A, B, branch equal G, which is going to be taken, then C, D, E, and F, and then finally G. So start out with thinking about where the branch is applied, then go ahead and fill in the timeline here for what happens executing this program where the branch is taken. Figure out what happens to the later instructions, and is this what we want? Okay, so in which stage is the branch output applied? Well, we can see here that it's applied in the memory stage. We take the results from the pipeline register and we apply them for the next thing, so memory. Now let's go ahead and fill in the timeline what happens with the program. Here we can see the program's already filled in. So in cycle 0 we put A in instruction fetch, and then cycle 1 it moves along all the way down the pipeline. Now in cycle 1 we're going to take the next instruction, which according to our program here is going to be B, and then B is going to go through the pipeline and continue all the way down through the rest of the pipeline. After that, we're finally going to get our branch instruction in here, and our branch instruction is now going to go through the pipeline as well. Now, what happens after that? Well, in the next cycle here, we don't know the result of the branch. Remember, we don't find out about the branch until memory. So in the next cycle, we're going to go ahead and execute instruction C. And then we're going to do D. And these are going to move through the pipeline. In fact, we're going to get E in the pipeline. And it's not going to be until this point, when the branch is in the memory stage of the pipeline, where we're going to know the outcome of that, and we're going to be able to change the next instruction to go to the right place, to jump to G. And so then we're going to go ahead and continue executing. And so if you look at what happened here, what happened with instructions C, D, and E, they got executed. Even though we had a branch which was supposed to jump over them, we still went ahead and executed them. So these instructions are executed, and is that what we want? No, it's not what we want. We wanted to skip those. We wanted to go directly from A, B, branch, and then skip to G. So how could we fix this? Well, what we need to do is when we figure out this branch here, we need to go in and squash these instructions. We need to get rid of them so that they don't actually execute. Now let's take a look at another way we could do this. So which of these programs are going to execute the correct code if this branch is taken? Well, let's go ahead and walk through what happens here. So we're going to do A and B and then branch equal, and it's the branch instruction we care about. Now, the thing to remember here is that we're going to get the branch instruction back all the way here when we're in the memory stage. So we have 3 instructions after the branch that need to not do anything, so that when we get the branch, we can then go on to the next instruction correctly. So if you look at what this pattern shows us, it shows us we need to have 3 no-ops in the program in order to make sure that we branch to the correct instruction. Let's try filling in the branch delay slots. So here's some code, and we've got a bunch of branch delay slots here so that we do the right thing. And the question is, can we move stuff around in order to make this code more efficient? So let's take a look at it. Let's look at our first instruction here. Can we move this instruction to after the branch? Can we move this down to fill in one of these branch delay slots? And the answer to that is no, we can't. Because if you look at what's happening here, we're generating the result of R1 here, and we're using that in the branch. So this has to finish before we get to the branch. So it depends on it, so we have to have that before the branch. Okay, so we can't move that one. How about these other 2 instructions here? Can we move them into after the branch? And the answer for that is yeah. The branch doesn't depend on these, and they're always executed. So every time you get go to the branch, you're going to execute these beforehand. We know that all these instructions are going to be executed every time anyways, because they come after the branch. It takes a while to resolve the branch. So we can go ahead and we can move these down here to after the branch. Okay, what about the last one? Well, this add, can we move it so that it goes after here? Can we move it into this branch delay slot here? And the answer to that is no, we can't, because this branch instruction is not executed unless the branch is not taken. So if the branch is taken, we're going to go back to loop. If the branch is not taken, we're going to do that. If we put this instruction in one of the branch delay slots, that would mean it got executed every time whether or not the branch was taken. So we can't do that. So now if you look at the result we have here, our loop now has 1 instruction here and then 2 of them afterwards. And so instead of having 3 no-ops, we've now got our loop down to just 1 no-op. So we've made our loop a lot faster.